Welcome. This is the third and the last live session before we go for the examination. I hope that you are preparing well for the examination and you have followed also the lectures and are practicing the assignment questions properly. Just relax, and I hope that if you are regular with the assignments, then you will be able to crack the examination too. Some of you have been interacting with me in the discussion forum quite often, and some questions I have received regarding the pattern of the questions to be expected in the examination. The pattern will be similar to the ones you have been having in the assignments, and if you are just looking into the pattern that you are finding that there are MCQs, MSQs, so similar kind of things are also there. Only thing is this, that in the assignments you have found that some of the questions are numerical, some of them are theoretical. So similar things will also be expected in the examination. So just follow those lectures properly, and the assignment solutions, and also please remember to look into the corrections I have made later to some of the lectures. So there have been some mistakes, some of the mistakes were pointed out to me by some of you, and I thank all of you for taking the active interest and letting me know the mistakes I committed. So I also made some corrections to those things. So please notice that you see those corrected lectures too before you come to the examination. Now coming to the assignments, by now you have completed all of the assignments, that is there are 12 assignments so far, and all the 12 assignments have been completed, and the dates are also over for the submission. Now the things are getting evaluated. So what I will do, that I will quickly go through some of the important aspects of these numerical problems. One thing I tell you, that I received one query regarding the reading of the values from the figure which was provided to you for the temperature entropy diagram. Now you see that the figure, one of the students told me that the figure was not very well read. Yeah, I accept that, and what happens that whenever we put the figure on the net, sometimes because of low resolution of the source file, that you do not see the figures properly. However, these figures are not very common. So I could not figure out a better source of the figures, so that I could not help you much. But what I did was that I resent one of the figures which one of the students told me that was not so much readable. What I suggest, that if you are getting such kind of figures in the examination too, just try to make the as good as possible by your naked eye the kind of values you want to read on the figures. And what happens that even if the figure is properly seen, you find that you have to do sometimes interpolations in the figures, maybe between two curves. So in that case, what happens that different persons may read differently, and different persons may evaluate and determine the values differently. So there will be some small variations in the values, not too gross, but small variations are expected. But when you are putting those values in the formulae, then the result you obtain will not be too drastically different from the exact result. So there may be some 2-3% or 5% difference here and there. It doesn't matter, because when you see the options given to you, you will find that the options are given in such a manner that those small variations are taken care of in the solution. So do not panic Just when you find that your result is not matching exactly with the result given in the solution or the options you are given, you choose the one which is nearest to the value which you have obtained. Okay? So, those things are always there, some kind of errors are there. So, I hope that those problems you will not be facing much of a problem to solve and get the solution of. So, with this now I come to some of the problems which I am sure many of you have done correctly. So, I start in a reverse manner. I start from assignment 12. So, let us see the assignment 12 first. Here we see this question that flow rate of propane in a propane refrigeration system with an evaporator duty of this much between these two temperatures, and we have been asked to find out the flow rate. Now, and this particular table has been provided to you, okay, to find out the various properties, and the solution is in a way quite straightforward because this particular system was shown to you in the lecture. So, you have to refer to this particular figure, and this kind of problem was also done in the assignment in the tutorial. So, you see that to solve this problem, basically you are making one energy balance, and if you know how to make an energy balance, you should not find any problem in solving this particular problem. Okay. Now, you see that here the energy balance has been done, and here you are getting the evaporator duty, like you are getting these enthalpies, the mass flow rates, and also as per this particular thing, you find that as I told you that this particular JT valve is generally isenthalpic process. That means the enthalpy at the inlet and enthalpy at the outlet are the same. So, here you find that H4 equal to H3. So, if you make this kind of things and if you can properly locate the temperature and pressure at each of the streams, then you simply have to read out the values of the H, that means enthalpy, and plug in the values over in this particular equation, and you will be able to get the Q evaporator in terms of this m dot H1 minus H4, and from this you can find out the particular m dot. Okay. So, this is the thing. Now, understand one thing, that here you have been given the whole problem in a particular set of units, that is the FPS units. Now, it does not matter what kind of unit systems are given to you, even if this kind of question is asked on SI system, or you find that sometimes there are some mixed units, some of the units are SI, some of them are FPS. So, you just before you start solving, you please make sure that you are putting all the units in the same system, then you will not commit any mistake in the final result. Okay. Now, let us come to the second problem. In this you have some gas pipeline which is NPS 16 pipe and schedule 10 which has a flow rate of this, and standard temperature is taken to be this 50 degree Fahrenheit and standard pressure as 14.7 psi, and the compressibility factor is taken to be 1, that is it is to be assumed to be ideal. Okay. And this then what is happening, that you have to you have been given that this compressibility factor is about 0.89 at a gas flow rate of 90 degree Fahrenheit and 1500 psig pressure. Now, you have to find out the flow rate of the gas. So, what kind of flow rate you will get? Now, here it is also, and these particular figures are there, this particular table you can see. This table gives you the nominal pipe size both in inches and millimeter, and then OD, ID and the schedule number as you know, this signifies the thickness of the pipe, and as per the thickness, as per the schedule number you are given the thickness also, and here are the weight of the pipeline per unit length. And based on this you have been asked to find out the flow rate and the flow velocity of the gas in some particular unit. Now, you see that here also first you put all the information which have been supplied to you, and one thing I again repeat that sometimes you may find that the information provided to you in the particular question may be in excess than what is required. Okay. So, it is that you put all the information whatever is given in the question, but also make a proper judgment that which of the information are needed to solve. You may not always need all the data that are given to you in a particular question. So, that you have to be very careful about, and never think that if you are not finding the use of certain data in the particular problem, so you are going wrong. It is nothing like that. Sometimes excess data are also given. On the other hand, if you find that some data may be missing in the question, it might sometimes happen. So, if you find some data are missing, but you can assume some judiciously, you can assume some values giving some reasons, and then you can solve it. So, generally it won't happen in such kind of examinations, we also check the things, but if in any case sometimes of this kind of thing happens, then you can go ahead with it with some justification, you can assume some data and do the solution. Unless you justify properly in the assumed values, then that will lead to some wrong answer, that you should be careful about. Now, here you see these in the lectures we have shown this kind of equations. These equations are coming simply from the gas laws, and in the gas laws, as you know, that you have to give corrections for the pressure and temperature. So, similar kind of corrections have been applied to this particular problem, and you are getting the actual volumetric flow rate in terms of the standard volumetric flow rate, standard pressure, standard temperature, standard compressibility factor, and other things P, T and Z have been given in the problem. So, you plug in the values and you will get the values of the volumetric flow rate. Okay. Similarly, now once you get the volumetric flow rate, it is very simple to get the velocity, and this velocity is the superficial gas velocity. So, in this case you have to take consider the cross section of the pipeline, and this cross section is found by knowing the inner diameter of the pipeline, and that inner diameter is found by subtracting twice the thickness from the outer diameter. So, you get the inner diameter, and from that you can find the area of cross section, and you get the velocity by dividing the volumetric flow rate with the area of cross section. Only thing one you have to be careful about, that when you get the volumetric flow rate in this cubic feet per day and then you have been asked to give the velocity in feet per second. So, first you have to do that, you have to first convert this cubic feet per day into cubic feet per second. Only then you should apply this formula to get the volumetric this velocity in feet per second. Okay. So, this kind of unit manipulations, unit thing you should be very careful about. The units are very important, and whenever you are doing the problems, solving the problems in the rough, then you should always put the units so that you do not commit any mistake in the unit, because if you put different wrong units, then you are going to land up with wrong answers. Okay. So, avoid any kind of mistakes on the units. This next question is similar to the one previous one. So, I will not go through this again. So, this is if you have done it and you find that similar kind of this kind of formula have been given in your assignment also. So, this formula you have to simply plug in the assignment in this thing, and you can get the values. Now, understand one thing, that whenever you get such big formula, it is not expected of you that you will remember all the big formula. Some of the very basic formula you need to remember, but if the formula is quite big, quite complex, in that case you are not expected to remember those formulae. Many of the formulae will be given to you without mentioning that exactly where to use it, but if you have understood the theory, if you have learned the theory properly, you should be able to pick up the right formula from the list of formula given to you. Okay? So, any complex formula will be provided to you for your convenience. You should just learn that where to use which formula. This you just make sure that you know. Now, here similarly this particular question is coming that it is also in because I taught you different types of method to find out the flow rates and the velocities, etc. So, these questions in assignment 12 were based on these different formulae, and all these different formulae you are just checking from the tutor in the tutorial problems also have given some formulae, given the solution also, or in the lecture notes, and you see that in this particular formula we are putting this, we have to find the Reynolds number value, and as per the Reynolds number we have to find the value of the F, and this F value we have to this was what was asked in your question, to find the value of F. Now, let me come to assignment 11, which was focusing on the refrigerators, and in this particular problem this particular figure was given to you. Yes, this figure is looking a bit hazy, but you know but still you can read it. If you magnify it, you can read this figure, and just as I told you that whenever you are trying to interpolate some values between the curves, so you use it as much possible with some with your naked eye only. You try to make the best possible interpolations on this particular figure, and as I told you that there might be some small errors, but don't mind, the solutions are quite dispersed, the options are quite widely varying. So, you should be able to get the right solution. Okay? So, don't panic. So, I hope that by now all of you know how to read these figures. I just repeat quickly how to read the figure. This is a temperature versus entropy diagram. On the this y axis you have the temperature, and this is given in Kelvin. On the other side it is given in Rankine. Okay? So, these are the two standard temperatures and in two different unit systems, and on the x axis you find you have the entropy. Okay? And here also on this top also you are given entropy. Again you see that these two systems of units are different. Here it is joules per gram per Kelvin, and here it is BTU per pound per Rankine. Okay? So, these are the two systems of unit which have been provided, and here you see that there are many lines, curves are there. Like for example, these particular curves which are coming from the left to right, these are the constant enthalpy lines. So, all these figures which are given to you 300, 200, etc., you see that here it is given, it is joules per gram. That means, all these numbers which you are finding here, these are all in joules per gram. So, these are constant enthalpy curves. Okay. Now, you also see there are some constant density curves like this. It is given as constant density curve, and here you see that it is gram per centimeter cube. So, all these their constant density curves are there. So, you find that different values of these densities have been given as you move from right to left. Similarly, there are many constant pressure curves also are there, like these particular things are constant pressure curves are there. From state you can find that here it is 0.1, 0.2, 0.3, 0.5. So, you can see that these are the, that means solid lines are the constant isobaric lines or the constant pressure lines, and the dashed ones are the constant density lines. Okay. So, if you are following these lines properly, you should be able to get the answers properly. Okay. And as I told you, this you see this dome structure is there. So, outside the dome structure you have this superheated region, and on the left hand side you have the subcooled region, and within this dome you have the mixture of vapor and the liquid. Okay. So, this is how these particular TS, that is temperature versus entropy diagrams are represented, and you can read as per your requirement. Now, so you have been asked for a simple Linde-Hampson refrigerator with nitrogen as the working fluid. It is operating between 290 K and this much pressure and at this pressure. Now, as you say, simple Linde-Hampson ideally is working isothermally from the compressor, because compressor is taken to be isothermal, and so only what happens, the pressure is changing from the compressor inlet to the outlet, and then what happens that in the simple Linde-Hampson, you know that we are using a compressor and then a heat exchanger and then a jetty valve. After the jetty valve, you are getting the cooled gas. Okay. So, the overall efficiency of the compressor has been given like this, and the heat exchanger effectiveness has been given like this. And so, you have been asked to find out the refrigeration effect. Okay. Now, again you see that this kind, all the formula were given in the lectures, so you have to plug in the formula here to find out the duty, the refrigeration duty. That means how much refrigeration can be created in a simple Linde-Hampson. And this one thing you have to be careful about, the kind of fluid which is being used. Here it is nitrogen, so we are using the TS diagram of nitrogen. Now, if the fluid is changed, this diagram will be different. So, you have to choose the appropriate diagram to solve this kind of problem. Next, we come here, these solutions have been given to you, that how to read these values. Then COP of the same refrigerator was to be determined, and again you see that for COP you first find out the work done. So, here you find out the work done, and this formula is also was derived from thermodynamics. So, after this you get the work done, then you can find the COP by knowing the duty and divided the duty by the work done. So, refrigeration duty by work done is giving you the COP. And figure of merit means that this is the actual COP, and if you know the ideal COP, then the ratio of the two will give you the figure of merit. Okay, that which is the nothing but gives a deviation from the ideal behavior. So, because you have found the actual COP and this is the ideal COP. Okay, and you see this is the ideal COP and this is the actual COP, and actual COP is much less than the ideal COP, that is expected. So, this figure of merit is the ratio of the two, that is the actual COP to the ideal COP, and this is the value you are getting for the figure of merit. The next problem was on Linde dual pressure liquefaction system using air as the working fluid, and it is operating between these two pressures, and these are temperature given to you. And because it is dual pressure, there are two pressures. So, intermediate pressure is this, and the intermediate stream is also there. If you recall the particular figure in the system, then you find that the intermediate stream is there, and intermediate stream ratio is given like 0.75. Okay. So, these are some of the properties which you need to solve the problem. This was also provided to you, and so the liquid yield was to be found out, and this is the formula to find out the liquid yield. Okay. Now, you see this particular thing, as we learned that because of this dual pressure, this intermediate stream, even though it is decreasing the yield, but it is also decreasing the energy requirement, compression requirement. So, overall we are getting a benefit. Okay. So, this is the yield for this, and then the work requirement is coming down. Now, you see this is the work requirement. Again, see all these things, that whatever refrigeration systems you have been taught, you will find that everywhere what we are basically doing, that we are basically applying the first law of thermodynamics. So, please learn this first law properly, and if you know this how to apply the first law, then you choose the proper control volume, and if you have chosen the proper control volume, there is no reason for you to commit any mistake in such kind of problems. They are very straightforward problems. Just you have to plug in the, once you have derived the energy balance equation properly, it is a matter of reading the values properly from the given diagram or given table and plugging in the values in the particular formula to get the answer. So, just learn the application of the first law of thermodynamics. Okay. So, everywhere you see that we are using the first law of thermodynamics to get the answers. And similar to the previous problem, here also we are supposed to get the figure of merit, and here this is the formula to get the figure of merit, and you are plugging in the values and getting the value of the figure of merit. Okay. And now I am skipping the theoretical questions, I am just focusing on the numerical questions in all these assignments. So, coming to the assignment 10, here we have a Carnot refrigerator. It is operating between these two temperatures, and this we have been asked to determine the coefficient of performance of the refrigerator. Now, you see that this is a very simple straightforward formula which you have been taught also in the thermodynamics perhaps. So, if you know this formula, you can get the COP. Now, you see this particular formula for the Carnot engine is very straightforward, very simple. So, this kind of formula are expected to be remembered by you. All this formula will not be given because which are very straightforward. For example, ideal gas law or the real gas law like PV equal to nRT or PV equal to NZRT. So, all this kind of formula will not be given to you. Some of these you have to remember. So, similarly, this particular formula for Carnot cycles should also be remembered by you. So, here you see that if you have been given all the high temperature, low temperature, that means the source temperature, sink temperature. So, once you know that source and sink temperatures, you will be able to find out the ideal coefficient of performance, that is for the Carnot cycle. Next is the minimum work requirement to remove this much amount of heat from a region at 12 K for a sink temperature of 310 K. Okay. And again you see that this is the formula which is again for the Carnot, and we are getting this particular value for the work requirement. Okay. And now determine the work requirement of an ideal isobaric source refrigeration that removes 2.5 kilowatt of energy from low temperature using some ideal gas. The source temperature varies from this to this, means 5 K to 25 K, and sink temperature is 305 K. So, here it is different that here the source temperature is not constant, source temperature itself is changing. So, this kind of problem was also taught to you in the lectures, and similar problems was also done to you in the tutorial. So, if you have followed them, then again you can find that this is a formula for this coefficient of performance, and for this isobaric refrigerator, and here you see that all these temperatures have been given to you, and you have to simply plug in the values of the temperatures, and the Q is given. So, you can see that this is the work done. So, nothing to discuss much here because these are some straightforward applications of some formula. Okay. Only thing is that you should know the significance of each of the data given to you. Now, coming to assignment number 9. Here these particular statement have been given and to solve questions 6, 7 and 8. So, here you see that you are given 100 kilomoles per hour of saturated liquid feed containing 30 mole percent benzene, and the boiling point given 30 mole percent of toluene with the boiling point given, and 40 mole percent of ethyl benzene, again boiling point given, to be fractionated by distillation to recover 98% of benzene at the top and 94% of toluene in the bottom product. Okay. and what have been asked, the column pressure is essentially atmospheric. The reflux return to the tower is at its bubble point, and the average relative volatilities have been given for 1 and 2. 1 and 2 means benzene and toluene, and 3 and 2 means ethyl benzene and toluene. Okay. So, what have been asked? You have been asked to find out the minimum number of trays using the Fenske equation. Okay. Now, this is a problem of multi-component distillation, and we said that there is a shortcut method to do is this, that we assume Hk and Lk. Okay. So, here similar things we are doing, that we are, because we have been given these in the formula, in the question we have been given the separation in terms of the benzene and toluene. So, we are putting this in this benzene and toluene terms, and we are if this from the formula for the Fenske equation, we find that we are plugging in the values of all this to get the value of the minimum number of ideal stages. Okay. And similarly, we have been asked the fraction of ethyl benzene removed at the bottoms. Okay. So, again you see that once you get this ideal number of stages, and then you have this alpha 1 3, you can find out by taking the ratio of the alpha 1 2 and alpha 3 2, and you plug in the values, you write the n min in terms of this component 1 and component 3, and you can find out that if you put the value of n min, which was found earlier, from this you can find the value of the F3W. Okay. So, again you see that is simply some manipulations we are doing here and there of the same equation. Okay. And next was asked to find the minimum reflux ratio using under root equation. This also you see that under root equation was also given like this. Okay. And here only thing is this, you have to find the, you have been given the reflux condition, and you have to given this Q value you have to find out. Okay. The feed is saturated liquid, that means the feed is this HL, HL is the saturated liquid. So, HF and HL are same, but these two are same, so Q is coming to 1. So, you put the value of Q over here and put the values of the various things like alpha 1 2, alpha 2 2, etc., etc. You see that you plug in the values of everything, and then you find that you are getting a quadratic equation in phi. So, now you see that these two values are coming, both are positive. See, phi has to be positive. So, now which one to be chosen? Now, it is like something like this, that this was taught to you that when one or more components do not distribute themselves between the top and bottom products, then phi is between these two, that is 1 and LKHK. And in this case, that your LK, as you know, that is light key and HK is the heavy key, and this HK LK concept we take for shortcut computations in case of multi-component systems. Now, in our problem, this benzene is taken to be the low key component, and toluene is taken to be the high key component, heavy key component. Now, because ethyl benzene has a molecular weight more than that of toluene. So, what we say that ethyl benzene is taken HHK, that means heavier than the heavy key. Okay. So, you see that we find this LKHK means basically this is 1 2. Okay. So, this 1 2 is given alpha 1 2. So, this alpha 1 2 is taken to be 2.4, which is the value of the alpha LKHK. So, these things were taught to you in the lecture. So, just follow the lecture, you have to find this value of this x1d, you have been find, and then you find the value of the xd2 and x3d, because the ethyl benzene is not there in the distillate. Okay. So, this is coming to 0. So, now this is the equation this V min equal to this was also derived in your lecture. So, if you see this equation, you get the V min value, and you plug in the values over here in the summation and get the value of this of V min like this, and once you get the value of D min, this distillate, then you see that this is the formula to find out the distillate flow rate. That means you are adding the individual flow rates to get the distillate flow rate. And once you do get the distillate flow rate, that means you know that this reflux ratio is the L by D, and if you do the overall mass balance, you find that L by D is given by R min plus 1 into D is equal to V min. So, V min you have found out already, so you can find the value of the R min. So, these are some simple formula, some of the formula were derived, and like for example, this kind of formula are derived from first principle. So, and this like the material balance to find out the reflux ratio, that material balance is quite straightforward. So, it is not that we will give those material balances to you. You are expected to remember the material balance, and even if you forget the material balance, if you know how to make a material balance, if you identify the control volume properly, I am pretty sure that you will be able to quickly derive this material balance to get this, to correlate this R min, D and V min. Okay. So, if you can derive it properly, you should be able to get the value of the minimum reflux ratio. Next we come to assignment 8. Here the sixth problem, assignment 8, here you are asked to find out the number of stages required to compress natural gas from this particular pressure to this pressure. Both are gauge pressures. This is very important for you to remember, because whenever the pressure is given in gauge, before you start doing the problem in case of compressor, you have to convert the gauge pressure into the actual absolute pressure. Okay. So, that is why it is important for you to note the unit in which the data have been provided. So, here you see that the first what we are converting the given pressures from gauge pressure by adding the atmospheric pressure, that is about 101 kPa, and to get the absolute pressure. So, these are absolute pressures, and these pressures will be used to find out this compression ratio. Now, understand one thing, you can see here that if you do not convert the pressures from gauge to absolute, then the answer will be definitely wrong. Okay, because the things are getting added, not multiplied. Had they got multiplied, it wouldn't have made any difference to you whether you multiply or not, but because they are getting added, so you will find that you will land up with wrong answers if you do not convert the gauge pressure into absolute pressure. So, once you have done that, then plug in this particular equation and you will get the number of the stages. Now, you see the number of stages is coming in fraction. So, it cannot be fraction. So, you have to take it to the kind of round it off to the next whole number, not the less one, which is the next above, that is 2.98 is taken to be 3. So, you need 3 number of stages to achieve this kind of compression. Now, here in this particular questions, you have been given the molar mass of natural gas, and the ratio of the heat capacities, that is gamma, is given like this. Compressor is taken to be 100% efficient, and the reversible work required is to be found out, and here to compress the gas from this to this pressure gauge, again it is, see, it is in gauge isothermally. This is very important, that whether because you know that work requirement changes whether you are taking isothermal or isentropic or polytropic, and depending on that the work requirement would change. So, you have to be very careful about each of the statements, each of the words and phrases given in the question. Read them properly, do not be in a hurry, do not skip any of the words and phrases, otherwise you are going to mess up the things. Okay? So, it is isothermal compression, and you have to use the appropriate equation to find out the work. okay, and initial temperature is given like this. So, again you see that because it is isothermal, so the inlet temperature and outlet temperature of the compressor is going to remain the same. So, it is 300 Kelvin. Again you convert the pressures from gauge to absolute by adding with the atmospheric pressure, and you see that this is the particular equation for work requirement. Even this particular equation can be derived very quickly. Okay. So, if you know how to derive this equation, just integral of the V dP and its ideal gas. So, you have to appropriately take the pressure volume relationship for ideal gas. If you plug in the things, so you should not be finding any problem in deriving this particular equation, because isothermal condition, that is PV equal to constant, that means P1 V1 equal to P2 V2, and ideal gas is again PV equal to constant. So, you can replace, when you are doing this integral V dP, you can replace P in terms of V or V in terms of P as the case may be, and you can derive this particular equation given to you, because here the data are given in terms of pressure. So, you will convert the volume in terms of the pressure and you will get this particular equation. Okay. So, this equation I feel should not be crammed, you should be able to derive it. Okay. So, better you practice it a bit so that you can get this kind of small equations without wasting much of time in cramming. Okay. So, if you now you please be careful about the unit of the universal gas constant. Now, this universal gas constant is something that you should remember, and in this case you know that this 8.314 is kilojoule per kilomole per Kelvin or joule per mole per Kelvin. So, be careful about the unit of the universal gas constant, and also be careful that when you are going for universal gas constant and when you are going for simply gas constant, and you perhaps know the relationship between the universal gas constant and the gas constant. Okay. So, I am just telling you that some tips for the examination, because many times these small things, but which are very important, are sometimes missed, and you see that you make some kind of silly mistakes in your examination. So, I do not want you to lose any marks because of this kind of silly mistakes. Okay. So, all these problems which I have just covered, which were not covered in the last live session. Okay. So, with this I again repeat myself that don't panic, just follow your lectures, follow your assignment, all the assignment solutions and any kind of corrigendum I have put on the web. Follow each and everything properly, and take all the tips which I have just provided to you now about the kind of commonly made mistakes by the students. So, if you keep those things in your mind, I am pretty sure you will be doing quite well in the examination, and you still have a few more days to go. So, discussion forum is always there open. So, keep interacting with me as much as you can, and get any doubts resolved quickly. Okay. And I look forward to having a very good success rate of the students and also very good marks of all of you, and I am pretty sure that you will be putting all your heart and soul to prepare for the examination and do well. And I wish you all the very best for the examination. God bless. Thank you.